Hey guys, good afternoon. Good afternoon, guys. Hello, hello. How are you all doing? Hi, guys. Yes, hi. Very good, very good. Very good, Danny. Very good, Franklin. All right, that's all we are doing, hanging in there. All right, so you can barely see that I'm here alive. So I'm going to uh, turn my video off so that I have better connectivity, better bandwidth. So, and then we start the lecture. Still one more joining. Okay, very good. Participation is not bad at all. So it is being recorded. Already recording is on as far as I can see. Yes. So let me start sharing the screen. I'll share the entire screen. So you can see that. All right, very good. We have one joining, will be 12. All right, so good afternoon, everyone, again, one more time. So tomorrow's lab is going to be NMR spectroscopy, right? You probably noticed that in the syllabus, NMR spectroscopy. And for that, we do want you to have a good amount of background knowledge to joining. Okay, let's give one few more seconds. All right. Good. Hey guys, good afternoon. Who just joined? We have not entirely started yet, so you are okay, but still try to join a few minutes before 5. Would be a good idea. So tomorrow's lab is going to be NMR spectroscopy. So you will be learning techniques how to take NMR spectrum, creating the sample, put the sample in the NMR machine, and take an NMR spectrum. So here are some good news and bad news. We started this new NMR machine, which is only a, is it 60 or 90 megahertz machine? So the lowest resolution lab version of this NMR machine. So a spectrum is not going to be looking very good. And I have seen the resolution was terrible, to be honest with you. But at least gives you a glimpse of what to roughly expect and some sense of NMR. It really is not very satisfactory. However, I generally have the TAs take you guys to a good NMR machine, which is in a different room. And generally, they make an arrangement with the NMR manager. I hope they did. I'm not entirely sure. I'll send them an email to see if they can. It also depends on the NMR manager, because this is such a sophisticated machine. It requires an extremely qualified person to be in charge and take care of it, maintain it basically all the time, every day. Even during COVID-19, someone had to go there every week, at least once a week, sometimes twice a week. Many of you have finished 263. Many of you I can recognize were with me, and you have some exposure to NMR spectroscopy, the theory part, which is what is expected of all of you. Although I know there are few of you who are taking 263 now, and I have done the syllabus accordingly. Oh, by the way, this semester I'm teaching both sections. So all of you are taking 263. As you notice, I have just finished discussion of NMR. Chapter is done. I actually made the syllabus accordingly, so that is already done. So for them would be a repeat and revision, and those who have taken earlier also a revision. which also helps me to make the points across very quickly, considering, as you well know, I take 4+ hours, like 2 days and sometimes slightly more than 2 days, to cover NMR spectroscopy, the whole thing. And here we have only 50 minutes, and as you see, 5 minutes is already gone. But still, I'll take few minutes longer. Generally, even in the lab, previous years, I used to give more than an hour lecture, often 90 minutes or so. So let's see how much we can do. It's going to be a little bit longer. Uh, but knowing that you have studied or learned it, it should not take the entire 4 hours. So that's a good thing. So as I said, the bad news is the machine itself. Good news, you will learn to make sample and to place it in the NMR machine. Big machine is significantly different, and but if they scan, they will take you there. Now, secondly, what you will be actually doing is you will be given some problems to solve, which is basically theoretical NMR, in the sense you will be given some problems generated by machines or from literature. You will be working on them in the lab to keep you engaged during this time so that you can figure out where they are. TAs are going to help you if you cannot. Keep in mind, NMR spectrum analysis is not something you take a look and figure it out. In IR spectrum, you see what functional group, 5 minutes job. Yeah, that's okay. However, NMR spectrum analysis is hours job. So do not expect to figure out right away. Do not immediately go tell TA, oh, is it this? No, that is not the approach. You have to do in a systematic manner, all the points, all the small details to figure it out, and then you come up with multiple choices, multiple possibilities, and then you narrow down slowly, one by one, based on the different aspects of NMR we are going to be discussing even in this short time. So whole process is meant to be a lengthy process, and you have to be patient and diligent and do slowly analysis step by step. It's like solving a difficult puzzle, not a children's puzzle, right? Your IR was a children's puzzle. This one is going to be more complex. Followed by, they will also give you few problems to solve at home, since you are not doing any other experiment. So your lab work is going to be solving some of the NMR problems. And again, take time. It is not meant to be solved in minutes. That is meant to require hours to do that. And that will be your lab report for the following week. So follow those things, what Alexis says and Wakar says. All right, and they're supposed to discuss together. So that's how it has been all these years. Only difference is we did not have a benchtop NMR that you are going to have this time in the lab, because that toy NMR only can run in the NMR in our lab. The professional NMR or say high resolution NMR requires special management, and they are cryogenic in the sense they are dipped in liquid nitrogen, some of them in liquid helium. So that is high resolution FT NMR. This one is not FT, this one is just a direct straight simple NMR, which should be more in line with the theory in a sense. So having said that, let's begin. So NMR, as you have seen this picture, those who are with me, NMR deals with, well, NMR full meaning is nuclear magnetic resonance spectroscopy. In this case, we deal with the nucleus. Yet there are few things are common with any other spectroscopic techniques. For example, one aspect is the resonance. Even in infrared spectroscopy, you have resonance. In a IR, okay, let me give you quick resemblance with NMR, only one small aspect, not the whole thing. So here I begin to write NMR spectroscopy that we do today, but I'll tell you as a quick reference, or not reference, I should say review. A quick review of IR. What you did, IR, IR works based on what is called vibrational transition. And you have learned before, I'm not going to go detailed, we don't have time for that. The molecules always vibrate because of their covalent bonds. Vibration is a motion that creates a kinetic energy, which is vibrational energy. And this vibrational energy, unlike Newtonian mechanics, they are quantized, meaning they have fixed vibrational energy state or energy level. So if I were to draw a diagram, this is part of a diagram, and or maybe this direction is going to be energy, and the molecules exist and different vibrational energy levels. So let's say here is vibrational energy level V0, then you have V1, V2, V2, V3, etc., etc., and it keeps going on and on and on and on. Many vibrational levels, right? Hundreds to thousands of vibrational level. So what happens, a molecule, because of its vibration, we are talking about the vibrational motion only, because of its vibration, it is at a certain vibrational energy level. What about that level is? Let's say that is somewhere like v n v m, let's say. I'm saying that because it's not such a small number, it's a large number. And then the idea is the vibrational transition is possible, meaning molecule can vibrate at a higher energy if the molecule absorbs the exact amount of energy. Then and only then molecule would be able to undergo a vibrational excitation, vibrational transition, which is to say molecule can go from vibrational level Vm to vibrational level Vn, for example, which means the energy difference between these two is going to be delta E equal to Vn, En, or Vn, I should say, energy of this. Write it again. Delta E is going to be equal to energy of Vn minus energy of Vm. That is the delta E that will be equal to h nu. Oops, very bad nu. And when this nu, the frequency of electromagnetic radiation, is such that h nu corresponds to the exact energy gap between these two levels, only then there will be vibrational transition. And then vibrating molecule will absorb that radiation and will vibrate at a higher vibrational frequency, right? That is vibrational transition. That is the understanding of spectroscopy in general. So there is also resonance. Resonance is when the vibrational frequency exactly equals the energy gap between the two levels. So that was vibrational transition and resulting in absorption of infrared radiation, right? That energy comes from IR radiation. So it is not just any frequency of radiation, this frequency of radiation in the IR radiation. IR radiation was, you have seen, between 600 to 4000 centimeter inverse, peculiar unit called wave number, right? So there is this transition, and that require the exact match. If you give a huge amount of energy, 10 times more than this amount of energy, no vibrational transition will occur. It has to be exact match. So it is one kind of resonance. So that was vibrational absorption spectrum you saw due to this vibrational transition. Keep that in your back burner. Now, when we come to, so that's that. Now, when we come to NMR spectroscopy, there are a number of things very different. First of all, we are not talking about the molecules resonance at all. We are going deep into the atoms. Not only atoms, we are going to the nucleus. Okay. However, by understanding and observing, let's say, interaction of nucleus, we are going to see how can get a huge amount of information about the molecule. What is the objective of NMR spectroscopy? NMR is to, the goal is to determine structure of organic molecules. Right? That is our actual goal. Structure of organic molecules. So how we get information about the whole molecule? By analyzing or seeing some interesting resonance in the nucleus. That involves even going further in depth with the nucleus. Okay? And it's not only just any nucleus. Yeah, it is the nucleus. Nucleus, as you know very well, it is positively charged, right? Why? Because it has proton, which is positively charged. It also has neutron. And surrounding that, you have electrons, but the electrons spin or motion is not in the consideration of this NMR at the beginning, although we will see how that has an interesting part as well. So nucleus has protons and neutrons together. They actually spin. They are spinning. They are spinning on their own axis. Such spinning nucleus consisting of proton and neutron, since it is charged particle, the nucleus as a whole being charged and spinning, it creates a magnetic field. Okay, but the proton is spinning, neutron is also spinning. However, this spin will have spinning motion in the nucleus is causing a magnetic field. However, it is only when the spin moment, not the time. Moment is a very physics term, many of you know. Moment basically means its magnetic strength and direction together. Sometimes it is given a symbol I. I will not burden with you various symbols. It has a certain magnetic moment. If I write I am like this, this magnetic moment is going to have and will have a resonance with in NMR when they have what is called a certain value, and that value is possible when this spinning nucleus has odd number of particles total, okay, which is what you call mass number. Proton neutron together is called mass number. These two together is called mass number. Mass number. When this mass number is odd, meaning 1, 3, 5, 7, etc., etc., when the mass number is odd, then the spinning nucleus will have a net magnetic moment. Okay, here I summarized in one sentence. When the spinning nucleus has odd number of particles, total number of particles, meaning mass number being odd, then in this spinning nucleus will have a net magnetic moment, which is Im, that is magnetic moment. So it will not have that if the mass number is not odd. That limits various nuclei. So fortunately, hydrogen is one that has odd mass number. So hydrogen 1 will have. Carbon 12 will not, but carbon 13 will have. So we will be discussing these two, and there are a few other elements also have odd mass number in their nucleus. The one with hydrogen, we will call it, as you say, hydrogen in the nucleus only has a proton. We are talking about the nucleus, and that is also why it is called proton NMR. So when you say proton NMR, the word you write as this. However, you do not say 1H NMR. That would be very novice and unskilled discussion. You would say, you will read as proton NMR because 1H refers to proton. So we'll be discussing this proton NMR. All right. So the spinning nucleus having a spin moment acts like a magnet, and because this moment, magnetic moment, is actually a vector quantity. Here is another interesting aspect of it, that magnetic moment is a vector quantity. Vector quantity, meaning it has both direction and value. Because it has certain direction at the same time. However, in normal circumstances, in a molecule, all the hydrogens having their own spin moment, having own vector, they are entirely random. So let me resort to some of these pictures. Here is a picture of a spinning nucleus. You see on the left hand side, it creates a magnetic field. Magnetic field will have a magnetic moment. Magnetic moment consists of magnetic strength as well as direction. Okay, magnetic moment comprises of value and direction both. The direction is shown with this arrow. So under normal circumstances, without the influence of anything else, they are random. However, if this randomly oriented nuclei in a sample of molecules in a test tube is suddenly placed in an external magnetic field, which is billion times more powerful than the magnetic field of a nucleus. Nucleus being very tiny, it is extremely tiny, whereas external magnetic field is billion times more powerful, stronger magnetic strength. So when these nuclei are placed in such external magnetic field, what happens? Suddenly their nuclear spin or spinning nuclei, their the direction or even the spinning suddenly freezes. Suddenly they freeze. But when they freeze, some of them orient the same direction as the external magnetic field, some of them opposite direction. So we will call the spin of the nuclei are oriented along the or aligned along the external field or aligned against the magnetic field. Magnetic field meaning the external magnetic field denoted by B naught. Here you see this orange color arrow that refers to the external magnetic field as well as its direction, because magnetic field is bound to have its own direction as well. So here we are seeing two groups of nuclei under this field. Some of them are aligned along, some of them are aligned against. Those that are aligned along, they are going to be of lower energy, more stable. Those that are aligned against are going to have higher energy. So one that are aligned along, lower energy, are called alpha state or alpha spin state of the nucleus, and those that are aligned against, slightly higher energy, will be called as beta spin state. So how that happens is this. Imagine here is the direction of the magnet B naught in this diagram. Look at the diagram only. Do not need to read this. I will post this PowerPoint so you can read later also or see the pictures you have in your textbook as well. But I will post it anyway. Not only that, I will also post a Khan Academy video. Khan Academy, some of you are familiar. He is an excellent teacher, an MIT professor, and MIT scholar. He teaches worldwide online in various topics. So he has everything about different topics broken down into small pieces. And he's an excellent, one of the best teachers in the world. So of course, you can read that later as well. But that has topic by topic separated or section by section. So here it shows our spin of a nucleus being along the field, and then if that alpha state, this one is called alpha state, by the way. I can also show in a separate diagram, or maybe I will show this one is also, this will occur. I'll come back to the previous one. This one doesn't make it clear. So it is showing on the very left, you said the energy. Energy is the axis for this, and it is showing B not equal to 0, no external magnetic field, meaning our spins are all random. When an external field is applied on this diagram here, B not equal to 1.41 Tesla, referring to an extremely powerful magnet, then our nuclei are separated into two states. The ones that are aligned are called alpha spin state, that are against beta spin state. There is an energy gap between them. So point is, can alpha state can go to beta state? Here is a similar idea as the one I had shown you, vibrational transition, except this is nuclear spin transition. So if you were to apply the energy which is exactly the same as the energy gap, energy difference between the alpha state and beta state, then there is exact match, then there is resonance. That is why nuclear magnetic resonance. So that is the resonance that is coming from. And then if that exact amount of energy is given, not more, very, very exact, this is quantized, it's extremely fixed, then there will be a transition from alpha to beta. We can call it spin flip. This spin flip occurs when there is resonance, meaning radiation energy is exactly the same as the energy gap between alpha and beta states. Okay, and the spin flip, when occurs, it absorbs, and that absorbed energy or absorbed radiation energy that is being measured then becomes similar to the idea of absorption spectroscopy. Okay, so especially the machine you will be using has very exactly the same principle, and the more powerful machine operates in a slightly different mechanism, which I can speak about later if we have time. What is showing on the right side of this diagram, if the external magnetic field strength is much greater, then the energy gap between alpha and beta spin state will also be greater. Okay, and so, but still spin flip can occur. Energy gap greater, meaning it will need slightly higher energy of the electromagnetic radiation. Which radiation would cause such spin flip? It is the radio wave or radio frequency radiation. Radiation from the radio frequency, it's called RF radiation or radio frequency. Radio frequency is the lowest energy of all various radiations. However, that gives you this very exact match, which is understandable because you're talking about individual nucleus so tiny you cannot even see that, right? You cannot see even with a microscope, right? Nucleus, you cannot possibly see that. You cannot see even atom. This is even far beyond that. Therefore, it requires a very tiny amount of energy, and that's why radio frequency radiation has that just that amount of energy. Any other radiation is going to have too much energy that will do nothing because it is quantized, mechanically fixed, cannot resonate with different energy. So, so that's that. So there is an interesting correlation between the frequency of radiation that is necessary with the strength of the external magnetic field is shown with the equation above. There is a new, the frequency is proportional to beta naught, and then again further shown, the proportionality constant is gamma naught over 2 pi. So there is a direct relationship. Higher the magnetic field strength, greater the energy gap, greater the radiation frequency. Even this greater frequency still is within the radio frequency region. For example, this one, 1.41 Tesla, corresponds to 300 megahertz radiation for the radio frequency, and the second one on the C or the extreme right, that corresponds to 500 megahertz radiation. You may also see something funny. It says 300 megahertz instrument. Interestingly, Anna, It is the radio frequency radiation that is used to name or label the NMR machine. The machine that uses 300 megahertz RF radiation is called a 300 megahertz NMR machine. Okay? The machine that uses 500 megahertz radiation is called 500 megahertz machine. So that is our instrumentation aspect. And also I explained what causes this uh, resonance and thus a spin flip. Okay, that's why you need radio frequency to cause the spin flip. When spin flip occurs, then alpha state turns into beta state, goes up. And this delta E equals h nu, and that nu happens to be the radiation, the frequency of the RF radiation, not anything higher. So that's that. You still took me half an hour to talk about the principle behind that. Just because you are in an advanced class, I need to indicate the actual machine works in a slightly different manner. Okay, let me show you this one first. So here you see there is a uh, big magnet, extremely powerful magnet is shown, North Pole, South Pole, and suddenly you dip in your sample from the top, which is it says sample. Here is this orange red color. You dip in, suddenly they separate into alpha and beta state. And then suddenly you turn on the radio frequency generator showing here in this block diagram, and that shows a coil surrounding this test tube, or actually it's NMR tube. It's thin tube, you will use that. So you turn it on, and when you turn it on, resonance occurs, spin flip occurs, and absorption occurs. That goes to beta state, and it creates a corresponding absorption signal. That signal is now amplified, detected, amplified, all these things. Finally, you get an NMR spectrum. Here is another version of the same picture. You can see the magnet sample goes from the top. Actually, big machine looks like this, although that is not the machine you have in your lab. This is a high resolution machine. Usually 300 or say 500 megahertz machine look like this. Whole magnet is encased in a huge big drum. Only from the top, you just put the sample in, and you turn in all the switches, turn in radio frequency generator, everything control goes in the NMR console. You work on the desktop and create NMR spectrum. An NMR spectrum in the end looks like this. It has a scale as you see in x-axis between 0 and 10, although 10 is not visible here, generally between 0 and 10. Also, funny thing you see, 0 starts on the right hand side, not on the left hand side. Okay, and the scale is called delta scale. Here you see delta H, meaning delta for proton NMR, this hydrogen meaning proton NMR. Unit is ppm, parts per million. We may talk about that very briefly. So, and you get some spikes, and that is your NMR spectrum you will be analyzing. Okay. As I was trying to say, that actual machine works in a very funny way and quite differently. However, I just need to tell you because you may know that later and they will think, oh, Boson never said that. In reality, machine operates in a very strange manner, completely contrary to the principle I have just discussed. Basically, actually, the sample is actually irradiated with an extremely powerful pulse, a very intense pulse of radiation of all different range of these frequencies, and they all undergo spin flip at the beginning. So you create a spin flip initially. So all nuclei of the all hydrogens go to the beta spin state. From there, then those beta spin state nuclei that are excited state, they are allowed to relax. This relaxation data is measured with time. These are called time domain data. Here you see your induced voltage signals in time. That signal is meaningless to us. We get no information, we understand nothing from this. It is called pre-induction decay. There is no other visible sign of spectrum. Okay. However, it has all the information necessary that is super concentrated in it, which is then filtered. Okay, filtered is the term. Sounds funny. Filtration you have to learn in lab. You filter with a filter paper. How do you filter signal? Well, this electronic information, also called time domain information, is filtered through a mathematical equation, highly advanced equation called Fourier transformation. And that Fourier transformation, mathematically done in this machine, it eventually transforms into the same NMR spectrum that you understand from without using such technical weirdness, so to speak. Uh, I apologize, you can hear some noise. Let me try to minimize that because some of you probably know from previous semesters with me that the guys that do this lawn, they know my schedule somehow. I did not share, of course. They will always start doing this mowing the lawn in front of my house only when I have a class. Can you believe this? So annoying. Okay. Let me see if I can close it. Ironically, I have never seen an exception. It's always when I teach, when the class is on, they start doing this. And even I had classes at different times. Still, that is what happened. Such a coincidence, such a nuisance. Anyhow, so going back to this discussion. So as I said, the machine operates in a slightly different way when you go to high resolution machine. However, the machine that you have in your lab, the same room where you have your IR machine, that operates based on practically the way I have said, which is not this Fourier transformation. There you have a fixed magnet and there is no Fourier transformation. You are causing a ring flip and that absorption is measured. So that pretty much corresponds to absorption signal that we are talking about. And that actually does not create good resolution. And that is the reason they do this weird manner, getting an opposite data free induction decay, because that produces a far better resolution and nice spectrum. Electronics is extremely complicated, extremely severe electronics goes with it. Anyhow, so coming to our NMR spectrum analysis, how can we understand an NMR spectrum? Especially biggest confusion comes from the very topic that all protons are absorbing the same radiation. If they are all absorbing the same radiation, why in the world would they produce different signals? You see, a very quick dilemma comes right away. Well, the answer comes from the fact that different protons in a molecule are not under same chemical environment. Different protons in a molecule are in a slightly different chemical environment. How so? That is what we are going to see in terms of how electronic environment is different. If the electronic environment is different, then their magnetic environment is different also, right? Those go together. They go hand in hand. So, for example, if I were to give you an example of a molecule, let's imagine the molecule CH3, CH2, CH2, let's say chlorine. Now, we have various protons. We are only talking about the protons. However, the protons that we talk, these three groups of protons, CH3, CH2, CH2, they are not of the same kind. They are not of the same type. How different are they? To understand that, we have to understand a very fundamental concept of shielding. What we mean by shielding? We mean is the nucleus. Let me write it on the right hand side. A nucleus as such, here it is, and we are talking about the nucleus is filling the external magnetic field strength B naught. Remember that we discussed, sorry, not B naught, that we talked about. So it is the nucleus that fills that magnetic field strength, right? And that creates a corresponding tiny bar magnet strength. It causes that corresponding induced vector or induced magnetic moment. However, these magnetic moments are not all of them are the same. Why? Because the nucleus that we are talking about, actually the nucleus is not alone. Nucleus is not naked. What I mean by that, nucleus is always surrounded by electron cloud. As you well know, surrounding a nucleus we have electron cloud, right? Electron is like a cloud, as you know. So here you have electron cloud that is negatively charged. While nucleus is positively charged, electron cloud is negatively charged. That is also a charged field, right? It is a charged field. Because of this charged field, negatively charged field, the nucleus at the center of an atom is not really feeling the same magnetic field strength given by B naught, because it is being shielded by the electron cloud that surrounds it. So nucleus is feeling less than what the applied magnetic field strength is, which means the nucleus is actually shielded from the external field by this electron cloud. So all nuclei are actually shielded. And interesting thing is, if we say all hydrogens are shielded, here comes the second aspect. All hydrogens are not equally shielded. If I show you, for example, these hydrogens in this nuclei, of course, they are highly shielded by their own electrons, right? However, the hydrogens that are next to this chlorine, they are shielded differently. Why? Because chlorine pulls electron, therefore the shielding effect on these hydrogens are going to be less, because electrons are pulled by this chlorine being electronegative element. If it pulls, that reduces the electron density or electron clouds density. Therefore, shielding is diminished to a great extent. Okay? Whereas the blue hydrogen that is far away, that is not diminished at all. So hydrogen in the blue is the most shielded. Hydrogen in the green is least shielded. Least shielded because chlorine pulling that electron cloud. Okay, this is the very fundamental basics of understanding NMR. Of course, the one in the middle is in between these two. That goes without saying. This is going to be something in between. Less shielded than the blue one, but more shielded than the green one. That is going to be something in between. So if I draw the sphere in proportionate way, then it is going to look something like this. So here you can see this one is most highly shielded, and I am showing with a much bigger color bubble. So that shows different level of shielding. It is because of that different protons are experiencing the external magnetic field differently. If they experience differently, they are going to resonate differently. Why? Because the, uh, because they are experiencing field different, so therefore they will resonate at a slightly different magnetic field strength. One that is most shielded, let me even write the word, this is the one most shielded, and this is the one that is least shielded. The least shielded. So result of which is this: the one that is most shielded, for it to absorb the same radiation and resonate, is going to require slightly higher external field compared to the green one. Think this way: green one is experiencing more among these things the most. Okay? But the blue one is experiencing less because it is most shielded. So how can it feel the same as green? if the external field is far greater. Get the idea? Here is a tricky thing. Imagine this way. Winter time, cold, you go out. Somewhat cold. Now, if you are going to be wearing just a t-shirt, you are still slightly shielded from the cold. T-shirt covers you. However, if you are wearing a thicker shirt, full sleeve shirt, you are more shielded. You will feel the cold less because you are shielded. Likewise, if you wear a heavy jacket, warm jacket, then you are most shielded. Then you feel the external cold far less. This is how you can correlate how the shielded protons are feeling, experiencing the external field far less. If it feels far less, you are going to have to up that external field to feel the same, which is to say, if you are wearing a jacket, you don't feel the same cold as if you are wearing t-shirt. But however, if you are placed in a refrigerator, very cold temperature negative, then you are going to feel cold even with your jacket also, right? Which means your external influence has to be raised in order to feel the same. This is another way to get the concept right. So which is to say they are shielded differently and they will absorb or resonate differently, producing different signals. So that involves two other things. What we compare with, since we cannot create an absolute scale requires a naked proton or naked nucleus that would be filling 100%. We don't have that. So what is done in reality, we are using the opposite extreme, something that is most shielded, which is TMS, or tetramethylsilane, which is a silicon attached to 4 methyl groups. It is the highest shielded situation because it is the highest possible shielding it has, that is the most shielded, that is used as a reference because that is going to require highest amount of external field for it to resonate. Everything else is going to require slightly less than that. That is why TMS is the most shielded and highest field to resonate, which even though it is highest field, arbitrarily that is given the reference number being 0. Slightly counterintuitive, but that is the way it is done by this physicist that who first did that. So on the very right side on the spectrum, you see 0 in the delta scale. That is for the most shielded proton TMS. Everything is less shielded than that. Less shielded, we are going to be using the term being deshielded. Deshielded, okay? So one that is less shielded than the other, we will also use the term deshielded, just to keep that in mind. So, so, so NMR spectrum is going to be indicating this shielded versus deshielded aspect or deshielded protons. I can use the same diagram and copy and paste to write on it. Copy it. So would be helpful for you. I am still giving you a super concentrated lecture. As you can see, it still requires a lot of time if I wish to cover the basics and take you to advanced level. So here is a spectrum. TMS corresponds to the being most shielded. Most shielded, and that is given the number 0. Everything else is deshielded compared to that. And that's why we can safely say this direction going from 0 to a larger number is being deshielded. These are for deshielded protons, protons that are deshielded. We are going to be looking into relative sense. On the right direction, we'll call it shielded because protons are shielded compared to the deshielded protons. Since shielded protons require, like TMS, I missed a T, right? Must. Shielded protons require upping the field. You have to up the field. That is also called upfield. They absorb upfield or they resonate upfield. Likewise, this side will be causing downfield because they are deshielded, they feel more, do not need to up that much. Okay, so upfield versus downfield, shielded versus deshielded. So we can also see the shielded protons absorb upfield where the delta value, the ppm value, ppm is the unit, scale is called delta, your delta value is smaller delta in ppm, and downfield direction would correspond larger delta unit ppm. So these are some salient features that goes with it. Okay. So for example, in this spectrum that you see, it shows a molecule CH3O CH2CN. The CH2, the pink color protons that are between oxygen and CN group, therefore more deshielded because pulled by those two electronegative environment, and that's why that absorbs downfield. Here is the B. Blue proton has less of that, that's why it is considered upfield compared to B, even though it is far more downfield with respect to TMS, because TMS being the most shielded. Okay, so smaller the value of this delta indicating more shielded, larger value corresponds to deshielded. So that's the basic understanding. So with that, you will, and as I said, I'm reviewing these things. You have learned this in lecture already. So there are 4 things to understand about a spectrum. You see how many different types of protons there are, number of signals, then position of the signal that corresponds to the different chemical environment, which is given the term chemical shift. And third thing is intensity of signal, also called integration, that gives you a proton count of each type, followed by splitting of signal, which is due to spin coupling, that tells us about the neighboring carbon's environment, neighboring proton's environment. Chemical shift, as we had shown, values range from 0 and 10. The scale is ppm. That is a ratio of how far an observed chemical shift or observed signal is downfield compared to TMS divided by frequency of the operating machine times million, that gives you ppm, meaning per million. So these are the 4 different aspects. So so you can also read from all these things, all the shielded deshielded situation, and the first aspect is the different types of protons. All these are also written everything in detail here. So different type of protons, as you have seen, the molecule I have shown here. Here you clearly shows it has 3 different signals. Right here, if I say A, this is B, this is C. Obviously, C is the most deshielded or least shielded. Least shielded and most deshielded has the similar meaning. Least, I hear it is written least shielded, which is to say most deshielded. Deshielded, similar meaning. Here is the most shielded corresponds to least deshielded. So that's one way to look at things. So So you can see that there are three different signals you should expect from this molecule, which you will practice with various molecules. Let's say here you have a molecule. How many signals do you have for this molecule? This is going to have many different signals. 1, 2, 3. This is 4 and 5. None of them are equivalent. Okay, 5 is methyl next to a CH2, but the distance from the oxygen is different. 4 is directly attached to oxygen, 2 is 2 carbon away from oxygen. That creates a small variation in their chemical environment and thus absorb at a slightly different magnetic field strength or slightly different chemical shift values. But likewise, if you have molecule like this, let's say how many signals this molecule has, what is going to be your answer? Can someone attempt to say quickly how many signals did you get for this molecule? I give you 2 seconds. Oh, people already beginning to answer. You seem to have done this course NMR study. Very good. Danny, we already answered. Exactly. So you are correct because here this molecule has symmetry. First of all, you have to look at this methyl group and this methyl group are the same. Both are attached to the same carbon, therefore they are equivalent. So that produces one type of signal. This is one, this is also one. This carbon has a hydrogen, that's signal number 2, and this is signal number 3. But the whole molecule has a symmetry. You see, right side of this diagram or this line is the same as that of the left side, meaning on right side this is also same as 1. This is same as 1. They are exactly same distance away from the oxygen, meaning their deshielding extent of deshielding is exactly same. So for a symmetric molecule, you have to look at carefully. So obviously the molecule is going to have 3 signals. This one you saw it has 5 signals. So this you would be able to see based on their chemical environment. A tiny variation makes a uh, different signal. Yeah, we'll give you aromatic example later on, MD. As you see, you still have limitations based on the timing. Let's see how far we can go. But still, we're going to take hour and a half anyhow. So second thing is when you have double bond, that is more important to understand more than your aromatic structure is the carbon-carbon double bond. If you have a molecule like this, and if I ask you how many signals would you have, can someone quickly indicate how many signals you might have for this molecule? How many signals? Genoseo said 5, MD said 5. Very good. Danny, you are silent, but that's okay. Yes, indeed, there are 5 signals because when you have a carbon-carbon double bond, you have to look at the fact that the 2 hydrogens attached to this double bonded carbon are not the same. One hydrogen, yeah, this carbon has a hydrogen also, by the way. So what happens is this hydrogen and this hydrogen are no longer the same because one is cis to this pink hydrogen, other one is trans to this pink hydrogen. Double bond being fixed, rigid, that makes this blue and green different. And then you have other signals, which is here you have a here is another hydrogen, and of course here you have another hydrogen, giving you a total of 5 different signals, right? So you have 5 signals. So anytime you have a double bond, you have to actually draw it out and see if cis and trans are the same or different. In this case, different. Unless if the both groups were ethyl group on the left side, instead of a pink hydrogen, if it was another ethyl, then it would be symmetric. Then you would only have uh, what is it called? Four signals. But here we have 5 different signals. Was there a question? Yeah. Okay, that's all right. So second, another aspect you have to look into when you have a ring structure. In a ring structure, number of signals is difficult to see very quickly. for a molecule like this, just looking at CH2, you cannot say that CH2s are always same, and thus distance from halogen is not good enough to make that calculation. How would you do that? In a ring structure, you have to draw out all the hydrogens that are present, knowing that in a ring structure is also a rigid structure. In a cyclopropane, cyclobutane, cyclopentane structure has an approximate molecular plane. Therefore, there is a up-down situation, which is what we have seen cis and trans isomers in cyclopentane or cyclobutane. Okay, so there is up or down, which means the hydrogen here is a hydrogen that is down, here is a hydrogen that is up. That is equally the case. This hydrogen up, this hydrogen down. Here is a hydrogen down, hydrogen up. So they have to be up or down, which makes us to see where the chlorine is. Chlorine is either up or down, does not matter which one you consider. If it is up, hydrogen down. If it is chlorine down, hydrogen up, which means the hydrogen that is up is not the same as the hydrogen that is down. They are different because the blue is cis with the chlorine, right? If you look at the chlorine as a reference, here let's take a look chlorine as the reference, then the blue hydrogen is cis, whereas green one is trans. However, the green one, whether it is trans or down, will be the same as this one. Okay, likewise this one, they are same carbon away. So here is you are having different type of hydrogens. Now in the same manner, this hydrogen is going to be different from the one that is below. That is going to be also different. So how many are we seeing? There is one still. This is a hydrogen. That gives you 1, 2, 3, 4, 5 different signals. So overall, you are going to have 5 signals. Okay, so that is every time you have a ring, and I have shown you with one exactly. You should work with other ring system 3, 4, 5. You should also try having an additional group other than one chlorine. If you have a methyl group or additional chlorine, that can be cis or trans, and work them out. This is advanced class. I will definitely challenge in those multiple ways, creating some extra thinking necessary. This is not a freshman biology class. This is an advanced level chemistry class. So you have to be challenging yourself as I am and be prepared accordingly. All right. So these are the different types of protons indicated. Let's look at this one. You may also want the protons can also be classified in another interesting manner. I ask you to read it from Klein's textbook because of the time limitation that we have here. So protons can also be separated as what is called homotopic. I just finished this lecture in 263 a few days ago, or last week in fact. Homotopic, this you will understand. If you do not, come to me whenever you can during my office hour or ask TA. Homotopic, and that is enantiotopic. Another is diastereotopic. These are all referring to hydrogens or protons. Protons. Homotopic protons, here is the interesting conclusion about them. Homotopic protons have same, by the way, they all refer to CH2s. They're all going to refer to CH2, by the way. They are all on CH2 hydrogens, 2 hydrogens when we have. So interesting aspect is homotopic protons have same chemical shift, same chemical shift. So it will not change your number of signals that we are talking about. Same is the true with enantiotopic protons. They also have same chemical shift values. Therefore, number of signals will be the same. Problem comes from the third one. Diastereotopic protons have different chemical shift values. that will add different number of signals. They have different chemical shapes. Okay. Uh, okay, Anthony. So go. You can listen to this later also, and also generally speaking, I'm assuming that tomorrow, before the actual lab at 12:30, you have free time. Yeah. Okay. Thank you, Anthony, for letting me know. But also, please do listen later on the next part. I will spend another 20 minutes or so. Um, and those who are remaining, including Anthony, though, I'm assuming that all of you have this 12:30 available, right? Hmm. Yeah, okay. Jangnam, that is also fine. That is also fine. All right. All right. So these are some interesting aspects. And main thing is the chemical shift, which is what we discussed. Chemical shift is the indicating their how shielded or deshielded values is. The one that is shielded that have larger chemical shift, larger delta indicating larger chemical shift. This delta scale is referring to chemical shift. Chemical shift values. Followed by the integration indicates how many protons of each type, like in this molecule I had shown. The first one, if we go for the very first one, this one, then the intensity ratio of the signals, or which is called integration, intensity of signals, intensity of signals is going to be 3 to 2 to 2, because you have 3 hydrogens of one kind in CH3. CH2 has 2 hydrogens of one kind, and CH2 green has also 2 hydrogens of one kind. So that is intensity. Last thing is the coupling, which is an extremely important thing about understanding the chemical environment and extremely crucial, which is, let's see if I can bring you there. Intensity discussion followed by what is called coupling. When I say coupling, what we are basically meaning, the hydrogens that we look at in a molecule, the signal we have been talking about, say CH3, CH2Br, you have only 2 absorption signals, but each signal is actually broken down into multiple signals, and that happens due to the any proton couples with the spin of the neighboring proton. That is why it is called spin coupling. So what happens if you have an absorbing proton and you have a neighboring proton, meaning a proton on the next carbon, like a scenario like this, pink proton being the absorbing proton we are discussing, has one neighbor. Neighboring proton can be aligned along the field or against the field, causing our original signal to interact with these two orientations and thus split into two. So one becomes two, call it a doublet. Okay, that's what we call it, a doublet. If you have two neighbors, here is the situation. Again, hold on. Those guys only make sound when I try to make calm. When you have two neighbor can be on same side or two neighbor can be two different side. Two neighboring proton can orient both being aligned along or both against, or one aligned, one against. If one aligned, one against, net effect becomes zero. They cancel out. If both of them aligned along the same direction as the external field, that is going along, equivalent to de-shielding, as opposed to aligning against corresponds to shielding. Shielding corresponds to upfield shift of the signal, resulting in the original signal to split into three. Since Cancelling can occur in two possible ways. That's why the signal intensity in this triplet will be 1 to 2 to 1. So 2 neighbor makes it 3. Likewise, 3 neighbor will make it 4. 3 neighbor can orient all 3 aligned, all 3 against, or 2 aligned, 1 against, or 2 against, 1 aligned, resulting in 4 signals. So basically, what we are seeing, the spin coupling results in, so which was the last item, spin coupling, also called spin-spin coupling, because spin of one proton is coupling, coupling only meaning interacting with the spin of the neighboring proton. So spin coupling results in signal splitting, and that produces a what is called a multiplet. Multiplet. A multiplet will be given by a simple equation n plus 1, where n corresponds to the number of neighboring protons. Number of neighboring protons. Okay. So that means if you have one neighbor, that is going to be 1 plus 1, 2 doublet. If you have two neighbors, 2 plus 1, 3 triplet, and so on, which is what you can see in this. If you have zero neighbor, meaning no neighbor, then n is 0, so n plus 1 is 1. That means it is a singlet, no influence. So the multiplets are indicated this way: singlet, doublet, triplet. 4 would be quartet, 5 is quintet, 6 is sextet, 7 is septet, octet, nonet, etc., etc. So that is the spin coupling discussion and spin coupling situation. So there are a number of examples here in this. So read through this. As I said, the TAs are also going to walk you through with trying to solve various uh, what is it called, various NMR spectra, help you analyze, apply all these things, and read this PowerPoint, read something from the text if you need to, and then apply that in some of the problems that will be given to you. One additional thing I would like to say, there is yet another thing called complex coupling. Complex coupling situation is when two neighbors are not the same. Let me give you two different examples to make the point clear. So for example, if I say, if we do not consider complex coupling, let's say here is a here is a molecule, and let's say here you have, I don't know, maybe a hydroxyl group, for example, talking about an alcohol. So if I say how many signals you are going to get, you can begin to count. Here is 1, 2, 3, 4, and 5. We have 5 signals, right? There are two additional points I want to make it to you. The proton attached to oxygen, they do not count. Sorry, they do not couple, I mean. They do not couple. So the alcohol signals and the amine signals, protons attached to nitrogen and protons attached to oxygen, they do not couple. Do not couple. So whatever the number of neighbor it is, they will always become a singlet. Okay, that will be singlet. So for example, if you are to try to calculate the multiplicities, you can try to do that, which is going to be a singlet, even though it has two neighbors. Okay, this will be singlet because hydroxyl proton do not couple. Now this one also will not couple with the proton of oxygen, it will only couple with the protons of the carbon number 3, for example. Well, this is not real nomenclature, I'm showing only the different types. So 3 has 2, so it is signal due to 4 is going to be a triplet. This is how you see you're using the rule n plus 1, the neighboring proton, not its own kind, but the neighbor. How about this one? What about 3? what is going to be its multiplicity? Well, now you have two types of neighbor. On the left side, you have has two hydrogens, right side also has two. So your neighbor is total 4. So therefore, your multiplicity is going to be 4 plus 1. That is a quintet. Quintet. Likewise, if I say what is going to be multiplicity for 2, one neighbor has 3, other neighbor has 2, total 3 plus 2 is 5, right? 3 plus 2 is 5, and that together is your n, and you have n plus 1. That makes it a total, that gives you 6. So that is going to be a sextet. It will be a sextet. One is going to be a triplet, etc. So this is the simple coupling we are talking about. This is considering simple coupling. Simple coupling. However, one quick thing to be indicated, that when you have a coupling, like I just showed, the gap between two coupled signals in the multiplet is called coupling constant, given by J. Here it is showing JAB. Okay, here is showing JAB, coupling constant, JAB. Now, here is an interesting situation, is that when you have that is my coupling. Now I'm going to talk about something extraordinary or unusual, is the complex coupling. A complex coupling occurs. Complex coupling occurs in some cases, not always. I'll give you one example where it certainly does. Let's imagine this molecule that I was showing. Here you have hydrogens, hydrogen. Here you have a hydrogen, and here you also have two hydrogens here, right? This is two hydrogens, and this is your hydrogens. Now, if I were to label the protons as this is 1, this is 2, this is 3, this is 4, this is 5, you are getting 5 signals. If I ask you the multiplicities for 5, you have 2 neighbors, that will be a triplet, understandable. Question is, what is the multiplicity of 4? When one neighbor is a vinylic type of proton like this one, vinyl proton meaning proton attached to carbon-carbon double bond, then this will result in complex coupling, meaning you can no longer say that we have 3 and 1, 4 neighbors, because these two neighbors are vastly different. So complex coupling occurs when two neighbors are vastly different. Now, when I say vastly different, that itself is a little bit ambiguous term. It not necessarily meaning they have they have totally different chemical shift, which they do, but there is additional rules to follow. Complex coupling having two different protons indicates this. Here is read this part in blue. Complex coupling is observed when this equation is met, which is delta of delta J, delta of delta, delta meaning the ppm scale, chemical shift, the chemical shift between the difference in chemical shift between the two neighbors divided by their coupling constant. When that is at least equal to 5 or more, then complex coupling occurs. Okay, so here is an unusual situation, and in advanced level you need to know that. So when you have this, of course, you are not going to know the delta J value in every case. Unless delta J is mentioned, you cannot possibly make that assessment whether complex coupling would occur or not. That's why I gave you one example when it would occur, which is when you have vinylic hydrogen. For this is going to have complex coupling. Complex coupling. When you have complex coupling, then the multiplicity is going to be not just n plus 1, we can say n1, one neighbor, plus 1, times n2, the second neighbor, plus 1. Okay, that is going to be complex coupling. In this particular example, it is going to be 1 plus 1, because vinylic hydrogen is 1, times other neighbor is 3, CH3 3, plus 1. As you can see, total becomes an 8. So you are going to see an octet. You are going to see an octet. Was there a quick question? So now not even 5, not even 6, you get 8. That results in 8. So N1 plus 1 times N2 plus 1. N1 is that vinylic hydrogen, N2 is this methyl hydrogen on 5. So that makes it total 8. Okay, and which, if you wish to understand why that happens, imagine, idea is when that equation is met, then different neighbors couple independently of the other. Here is the main part. They couple independently of the other, which is to say, if I say n1 neighbor being 1, that is going to split the signal into 2. Here is 1 and here is another 1. That is from our n1. But because n2 also couples separately and independently, n2 being 3 protons, so that each one is going to become a quartet. So it will be a quartet, and other one also turning into a quartet. So you have basically 2 quartets together. That is what is equivalent to 8. So that is what complex coupling is. Got it? All right. So as you can see, I have to give a long lecture in a short period of time. I hope you are able to follow. The very last thing, I'll take only 1 more minute to indicate that carbon 13 NMR is also in your discussion. Carbon 13 NMR refers to carbon only, very simple to discuss in a 1 minute, because, for example, a molecule like this, when you have 2 types of protons, but it has 3 types of carbons. Carbon being carbon 13, not carbon 12, carbon 13 being only 1% of naturally occurring carbon, it requires higher field. That's why the scale is between 0 and 200. However, the shielding, deshielding concept, upfill, downfill concept all remain the same, just a larger scale, and it is the carbons that we are looking into, not the hydrogens. Second thing was the intensity of signal or the integration. Integration has no meaning. This molecule has 3 types of carbons, but their heights are different. So height or intensity has no value. The chemical shift is, of course, based on their shielding and deshielding. Last thing about coupling. For carbon 13, you do not see coupling, because the chance of 2 carbon being carbon 13 at the same time is extremely rare, very small probability, therefore that will not be noticed. So the only thing you are learning is how many types of carbons there are, and which one is shielded and which one is deshielded. That's all about carbon 13 you need to know for this moment. All right, guys, so this is where I'm going to end the discussion. Still, I finished in less than an hour, which is surprising. Generally, even in the lab, I give 2 hours lecture every year. Okay, I borrow time from the actual lab. So this time, being online, we covered it here. So those who are not here, I strongly recommend listen to this and also study from the text. And also, as you know, this is only reviewing what you are supposed to have learned from 263. There is no other excuse either. All right. So that's about it for now. Have a nice class. I will mention next week that after next week's lab, we are going to have 2 weeks no lab. Very funny. We'll talk about that later. All right. So have a good night. If you have any quick question, I'll be happy to answer. You're welcome, Danny. Thank you too. Good night, everyone. You're welcome. Welcome. Thank you too. Bye bye, Anastasia.